Hey guys, welcome back. We're going to talk about today the margin of error for proportions. So going back to our example of the sea fans infected with aspergillosis, or however you say that, I have no idea, from sea fans that were in the Las Redes Reef and the Yucatan, if we want to try to estimate what is the true proportion of sea fans that are infected, what we did is we went out, we randomly sampled several locations, and we went out and we gathered samples from a randomly selected 104 sea fans. Then we saw which ones, tested them, saw which ones were actually infected. When we did it the first time, we found there were 54 out of 104 sea fans that were infected. That's where we got our sample proportion. And then from that, we were able to build a confidence interval with some certain degree of certainty or confidence, whether it be 90%, 95%, or 99%. Those are usually the confidence intervals that we use, degrees of certainty. But if we went out and we did it again, we wouldn't expect to have exactly 54 out of 104 again. Maybe a second time we do it, we would have another random sample that would give us 45 that were infected out of 104. Or maybe we would do it again and we get 51 out of 104. So we understand each sample is going to vary from sample to sample. The question is, how much variation will we expect? Well, that comes from the standard error, right? That's going to be our margin of error, or standard error, which is how much from the sampling distribution model from sample sizes of 104 with some sample proportion given, how much variation we would expect. And then we know however many standard deviations we go out will tell us what % of all samples we would expect to be within that. So that's what we're going to be building our confidence intervals off of the margin of error from our samples. All right, so the true proportion, whatever that value is, again, like it exists. I mean, that value exists. There's a certain % of sea fans in Las Redes Reef in the Yucatan Peninsula that are infected with aspergillosis, like even right now. But that proportion is different than what it was when we talked about it last week. It's constantly changing, and so it's kind of honestly impossible for us to know unless we are able to take a census of all the sea fans. It's impossible for us to really know, and it's always changing anyway. But we can still draw inferences from our samples and create a confidence interval with certain degree of confidence and come up with an estimate of what we think that value is going to be. So the true proportion, our samples we know will vary from our sampling distribution model of sample size 104. Our samples will vary with a standard deviation given from our standard error in this case, which is going to be P times Q, which is our sample proportion. Now, if we're doing our standard sampling distribution model, we should actually be using the true proportion and the true P and the true Q, right? Probability of success and failure. But we don't know what those are. So instead we use our next best thing, which is our sample proportion, which is our closest estimate that we have to the true proportion. So we call it the standard error instead of standard deviation because we know it comes from, it's not going to be completely correct because it comes from the sample, and we know the sample is not exactly the same as the true proportion, but it's close enough, or the closest thing that we have, right? So anyway, we know that the sampling distribution model with a sample size of 104 should vary with a standard deviation of about 5%, centered at the true proportion, whatever that true proportion is. Now, our sample proportion was roughly 52%, which is slightly more than, or maybe less. We don't really know. But what we do know is that 95% of the time it's going to be within 2 standard deviations of the true proportion. So it could be basically roughly 10% less than the true proportion or up to 10% more than the true proportion. And if our sample proportion was within those 2 standard deviations, then whatever our sample proportion is going to be, if we create a margin of error that's 10% on both sides, then that confidence interval will successfully capture the true proportion 95% of the time. So even if it was 10% too low, if we still go up 10% with our margin of error, adding it to it on the right side, it's still going to successfully capture our true proportion. So what we do is we take our sample proportion and we're going to add and subtract the margin of error, which our margin of error is going to be our standard error multiplied by some critical value. And the critical value is going to be like a z-score, which is basically how many standard deviations we're going away from the mean, deviating from the mean, multiplied by the standard error. So that'll give us the exact percentage amount that we're going to add and subtract. In this case, it was roughly 10%. All right, so let me kind of give you that idea of multiple samples again. So if we have a 90% confidence interval, which is going about 1.68 standard deviations away from the mean, which we'll calculate that in a little bit. So 90% of all samples should be within 1.68 standard deviations from the mean. So if we take our sample proportion and then we go that many standard deviations times our standard error from adding and subtracting it, then we should successfully capture the true proportion 90% of the time. So notice this sample portion is within this range of 90%. So when we take that range of 90% from our sample proportion, it's going to successfully capture the true proportion. Okay, so and then if we took another sample, this sample again was within the 90%, and so its margin of error successfully captured within that confidence interval the true proportion. And I take another sample, and the same thing's going to happen because it was within 90%. And again, 90% of all samples we would expect to be within 1.68 standard deviations of the mean. So its margin of error in this confidence interval would successfully capture the true proportion. And as I keep taking multiple samples over and over and over again, this one over here did not successfully capture the true population because it was more than 1.68 standard deviations away from the mean, which would happen roughly 10% of the time. And this was just one of those 10% of the time. So whatever level of confidence we want to have is nice because a smaller confidence interval, the less confidence we have, the smaller confidence interval means more precise. But it also means that 10% of the time we're going to be wrong. And we don't know if we got one of the 90% of the time that it worked successfully or if 10% of the time we're wrong. And we would call that actually a type 1 error, which is also known as a false positive. So anyway, we don't like that. So it just depends on what level of confidence do you want or certainty do you want and what level of precision. Those two are kind of trade-offs between the two. So as we took more and more samples, you notice most of them, 90% of all these samples would be within 1.68 standard deviations from the true proportion, and so they would their confidence intervals would successfully capture the true proportion. But again, this one, because it deviated further than 1.68 standard deviations from the mean, the true proportion, then our confidence interval would have failed on that time. All right, so as we keep going over and over again, here's another one that failed. So we would expect roughly 90% of all these confidence intervals to be successful. But we don't know. We're only going to take one sample, so we don't know. And if we took more than one sample, what we'd actually do, say we took two samples. So if I go back to my CFAN example, so let's say I went down and sampled 3 times, 104 CFANs, and these are the ones I got. Well, instead, what we would do is we'd actually add all these together and get the total number infected divided by the total sample, which was now going to be 312, right? And once we increase our sample size, if we quadruple the sample size, remember that's going to cut our standard deviation in half, which means our confidence interval is going to have half the margin of error. So if we do sample more than one sample, then we might as well add them together to increase our level of precision that way by just increasing the sample size. Okay, so hopefully you get that. Let me show you another way here. So our confidence intervals, again, the true proportion, that's remaining constant, okay, even though technically the number of CFANs are going to change. So some are going to become more might become infected, or some of them might die. New ones might grow that are not infected. So it's going to change all the time. But for the sake of this, we'll say that the true proportion remains confident. It's our samples that are going to vary, but we only get one shot, really. We're only going to take one sample. But 90% or 95% of samples, depending on what our confidence interval is, our confidence level would be, then like in this example, if we're doing 95% of all, if we go 2 standard deviations, in other words, 95% of all the confidence intervals would successfully capture all these true proportions. Now, if you notice, this one was too far away from it, so it didn't successfully capture it. This one didn't either, and this one didn't. But if we would have made that a 99% confidence interval, that would increase our margin of error, and then those probably would have captured it. And then we would expect 99% to capture it. So formally, what we mean is that 90% of samples of this size will produce confidence intervals that successfully capture the true proportion. This is correct, but it's a little long-winded, so we usually just say we're 95% confident that the true proportion lies within our interval. So our uncertainty is about whether the particular sample we have at hand is one of the successful ones or one of the 5% that fail to produce the intervals. So we don't know if we get one of the bad ones that are just so happen to deviate far enough away. 5% of the time, we would expect that to happen. That's totally normal. We just don't know if we got one of the 95% of the time that was successful or one of the 5% of the time that was not successful, which would be a type 1 error in this case. Okay. So the next question we have is, how do we find those critical values? So I was saying 1.68. Okay, apparently it's actually 1.645, but it's been a whole year since I last taught this exact topic, so I didn't remember, but that's okay. So 1.645 standard deviations going to the right and to the left, that z-score is what it really is. It's a z-score. How many standard deviations above or below the mean? That's going to be our margin of error. And so the margin of error is calculated by taking the critical value, which is what we call it, the z-score, for that specific level of confidence, multiplied by the standard error, which is basically whatever the standard deviation is. And that'll give us the actual percentage that we're going to be going. So to find these critical values, we can put it into our calculator, and we're basically using a normal model in this case. And so we want to use the inverse normal model measured from the center to find out how far do we have to go out, how many standard deviations we have to go to the left and to the right in order to have 90% of our area within the middle of our bell curve, meaning we have 5% left on both sides, in other words. Okay, so I'm going to do second variables, the distribution, and then I'm going to go to the inverse normal, and the area I'm looking for is 0.9, which is 90%, and I'm using z-scores, so centered at 0 with standard deviation of 1, because that's our standard normal. And then I'm going to center it, or measure it, not from the left, not measuring from the right, but measuring from the center, and that'll give me my critical values of basically 1.645. So if I want to do the same thing, we'll go to the next slide here. So that was what we had there. If I want to find the critical value for 95% confidence, so how far would I have to go out? What's my margin of error, right? How far do I have to go out in order to have 95% confidence? So do the same thing, except have an area of 0.95. So second, distributions, inverse normal. Our area is 0.95, and we're going to measure it from the center. All right, which is basically 1.96. So earlier we were saying it was 2 standard deviations. It's really close to 2 standard deviations, and that was from our empirical rule, the 68, 90, 95, 99.8% empirical rule, right? So roughly 2 standard deviations, but if we want to be precise, which we will from here on out, we'll do 1.96 for our critical value. So that's how many standard deviations we have to go out. See, it's almost 2 standard deviations. All right, then for a critical value of 99% confidence, to have that level of certainty, we have to lose a lot of precision, which means we're going to have a very large margin of error, just a really wide range of values. So to have 99% confidence, let's go to second distribution, inverse normal, 0.99, same thing. Ooh, make sure we measure it from the center. All right, now we have to go 2.58 standard deviations from in both directions. So adding and subtracting that times our standard error, which comes from our sampling distribution model. Okay, so if we were doing that with our C-fans, basically we would estimate with 90% confidence the true proportion of C-fans that are infected in the Las Olas Reef was anywhere between basically 43.8% and 60%. If we wanted to have 95% confidence, we would say, going now, 1.96 standard deviations, multiplying that critical value times our standard error, which is what each standard deviation is, would be, we would say that we believe we're 95% confident that the true proportion of Las Olas C-fans that are infected is anywhere between 42.3% and 61.5%. If we want to have 99% confidence that we successfully captured the true proportion, which would have a lot of confidence but not a lot of precision in this case, then we would have to go 2.58 standard deviations in both directions, multiplied by the standard deviation, which would give us, the actual percentages, which would be, we would say that we are 99% confident that the true proportion of C-fans in the Las Olas Reef that are infected with aspergillosis, or whatever, how do you say it, is anywhere between 39.3% and 64.5%. And again, 1% of the time we could still be wrong, so it could be just slightly more than that or slightly less than that, but 99% level of confidence is pretty good. Now, if we wanted to decrease our margin of error, one of the ways we could do it is by increasing our sample size, because that would decrease by the inverse square root law, would decrease the size of the standard error, because our sampling distribution model would all of a sudden shrink. All right, so this brings us to this lovely cartoon here. So the difference between, or basically the contrast, or the trade-off, that's the word I'm looking for, between certainty, precision, and sample size. So here we go. So tomorrow, I'm taking a look at tomorrow's weather, which is crazy because I believe tomorrow's weather is like -4 or something like that. So yeah, I hope you guys are enjoying your snowpocalypse going on here. The high temperature, so the guy on the weatherman says, the high temperature will be between 40 below 0 and 200 degrees above 0. And then smugly, Garfield says, this guy's never wrong. So that's true. He's never wrong. But also, look at that ridiculously large margin of error he has. Of course, the weather is going to be between -40 and 200 degrees above, because we've never had weather that was beyond that, right? So he's never wrong. That's true. So we have a lot of certainty that he's going to be true. But his margin of error is so long, it's not very precise. That it's not very helpful. So it's a trade-off between the amount of certainty that you want to have, which are we okay with being wrong and having a type 1 error, like sending an innocent person to jail, which we'll get to that in a little bit. I know it's terrifying. But at the same time, what's a trade-off if we don't? If we don't have that level of certainty, then we won't have any precision. We won't have a powerful judicial system to put people away. So we'll get to that more later. So how can we increase both at the same time? How can we have more certainty and more precision? Well, to do that, you have to increase the sample size. But the reason that we often don't increase the sample size is because it costs dollar bills. And so it just depends on your budget. And again, a larger sample is not necessarily always the best thing. I mean, while we're down there sampling our C-fans, we could have just sampled all the C-fans we could find in one area, but then we're doing a convenience sample, and that just really tells us what's going on in that area instead of giving us a good, accurate, representative sample of what's going on in the entire Las Vegas Reef. So again, it's all a trade-off, right? That's the real world. All right, so a 1 proportion Z interval is what we're calling these that we're making, because they're based on proportions and a single proportion. We'll do all the rest of those that you see in the calculator, by the way, before the end of the year. So like within 2 months, you're going to know what all this stuff is. Oh my goodness. Except for ANOVA. I don't know what that is. That's a new one from the last update. But anyway. All right, so it's called a 1 proportion Z interval. The reason it's a Z interval is because it's built around a bell curve, which is built around Z scores, which are like our critical values, okay? That's also why you see the Z scores showing up here with our margin of error. It's our critical value times the standard error. So we take our estimate, which is basically our sample proportion, then we're going to add and subtract the margin of error from it, which is going to be found by the critical values, which again are the 1.645, the 1.96, and the 2.57. which is our critical values, depending on the level of confidence we want to have, times our margin of error, which the margin of error is found by our p hat times q hat divided by n. And again, the reason it's the standard error instead of the standard deviations, which is from the sampling distribution model, is because it's based around our estimate, which we know is not going to be exactly right. But it's the closest thing that we have, because no one really knows the true values. Or if we did, then why are we doing confidence interval in the first place if we knew the true values? All right, so levels of confidence, 90%, 95, 99%. These are the common ones you'll see. The critical values are here. If you forget how to do that, just do the inverse normal and find them again. No big deal. All right, standard error again is calculated. It's called standard error because it comes from our estimate and not the actual true proportion. So we know it's not going to be exactly right, but it's close enough. Number 18. So starting the assignment, not too long. We'll try to make it a pretty short video today. Junk mail. Direct mail advertisers send solicitations, aka junk mail, to thousands of potential customers in the hope that some of them will buy the company's product. The acceptance rates is usually really low, quite low. Suppose a company wants to test the response to a new flyer, and they send it to 1,000 people randomly selected from their mailing list of over 200,000 people. So they have 200,000 people that they're trying to send it to eventually, but first, before they send it to 200,000 people, they want to send it to 1,000 people to see what kind of a success rate they can expect. What's the true proportion of those 200,000 people that they're going to send the flyers to, what's the true proportion of those that we are going to have that are going to respond? Now, based on the sample of 1,000, that will give us an estimate, which again, we can create a margin of error. From our margin of error, we can create a confidence interval to estimate the true proportion out of the 200,000 that will respond. Okay, so remember, we got our population, we've got our sample, population parameter, and the sample statistic. All right, and we're going to use our sample statistic to basically make an inference about the true proportion with a certain degree of confidence and a certain degree of precision. So they get orders from 123 of the recipients. So of the 1,000 people they send out, 123 of them responded. So check your conditions. Is a confidence interval appropriate? So before we can actually do a confidence interval, we have to make sure that it's plausible for independence, for them to be independent. So if one person responds favorably and buys something from their ad or whatever, from their flyer, then would we expect that to influence the next person to buy one? So if these are all separate households, then they should all be independent of each other. Some issues that we could run into is that if it wasn't randomly sampled, so if we send them to 1,000 people who lived in one area, who we know are more likely to buy it, then that would not be representative sample, right? So independence should help us with, if we do a random sample, it should help us with independence. We just need to make sure that it's reasonable to believe that they would be independent. And so I'm going to go ahead and say that each person's decision should be unrelated to the other. As long as they're not related, it should be okay. So, and again, a random sample helps with that. And another thing is that as long as we're sampling less than 10%, because we are sampling without replacement, we didn't send 2 flyers to the same person, that would be kind of silly, right? As it's really not truly independent because we're sampling out replacement. So whenever we remove those marbles from the bags, the probabilities are going to start changing. So as long as it's less than 10%, then we can override that independence assumption with the 10% condition, which we will do. All right, so random sampling condition. They said that they were randomly selected, so it should be representative of the 200,000 people as best we could. So we're good to go. A 10% condition, so we know it's not actually truly independent because we're sampling our replacement, but 1,000 people is less than 10% of the total population of 200,000 people we're going to eventually send it to, if it's profitable. The success failure, basically, do we have enough successes to guarantee 3 standard deviations unmolested by 0 or cut off by the hard bound of in as well? And so we have 123, which is certainly more than 10 orders, so we're good to go. And then the number of failures clearly is going to be more than 10 as well. All right, so create a 90% confidence interval. So what's lovely about this is our calculator will do it for us. So if we go, I'll show you where I got here. So go to, not that, go to stat, arrow to the right to test, and then towards the bottom, we have a 1 proportion Z interval. The number of successes we had was 123 people ordered out of 1,000. And we want to have 90% confidence. So the confidence level or C level is just going to be 0.9. Then hit calculate, and it'll do all the work for you. So it's going to give it to you in interval notation, which is totally fine. So I just wrote that here and did a little bit of rounding. What that means is, if I write it kind of more mathematically, we believe we're 90% confident that the true proportion of people that will buy from our ads are going to be between 10.6% and 14%. 10% of the time we could be wrong, but 90% of the time the true proportion is actually going to be between these two, because the amount of variation we would expect from the sampling distribution model of a sample size of 1,000. Okay, so explain what this interval means. So again, we are 90% confident that between the true proportion of people who will buy our ads is between 10.6% and 14% of people buy something. Explain what 90% confidence means. That means, well, I'll just read it. We expect the true proportion P to be within the margin of error of the sample proportion for 90% of samples of 1,000. So we don't know if this is one of the 90% of the samples that was successfully within the margin of error of the true proportion, or if this is one of the 10% of the times that our sample proportion is going to be without or outside the margin of error from the true proportion. So anyway, good to go. E says the company must decide whether or not to do the mass mailing now that they got their confidence interval. So basically, you go out, you do your sampling, and you go back to your boss and you say, hey, here's the confidence interval I have. And he says, well, how many people are going to do it? It's like, boss, that's not how this works. Let me give you a confidence interval, a range of values. What level of confidence you want? He says, 90% of the time, I want you to be right. So you give him a 90% confidence interval, you plug it in your calculator, and you say, hey boss, 90%, I'm 90% confident that the true proportion of people who are going to buy something from our ads is going to be between 10.6 and 14%. He says, wow, that's a lot more than I expected. And so you ask him the question, well, how much is it going to cost? And he says, well, as long as 5% of people buy something from our ads, we believe that it would be profitable to send the ads out. Well, then you tell him, oh, well, 5% is clearly not within my confidence interval. It's not within the margin of error of our sample. So we believe the true proportion is definitely well over 5%. So I'm at least 90% confident, or even more, and we can find that value later, the p-value, that we're going to make money on this. So let's go ahead and send them out. So what does the confidence interval suggest? Because 5% is not contained in our is not within the margin of error of our confidence interval, or it's not contained within the confidence interval, then we should mail the ads, because we don't believe 5% is a true proportion. That's the true proportion we believe is between these two values, 90% of the time. All right, number 10, parole. A study of 902 decisions made by the Nebraska Board of Parole produced the following computer output. Assuming the cases are representative of all cases that may come before the board, what can you conclude? All right, so Z interval for proportion. I don't know why those have weird spacings there, but with 90% confidence, they believe that the true proportion of cases that are granted parole is between 56.1% and 62.5%. So what can we conclude? Basically, just write that out as a sentence. We believe the true proportion of cases granted parole with we're 95% confident it's between these two values. So here we go. We're 95% confident that between that number and that number of people are granted parole, I guess, in the state of Nebraska. All right, so that's it. Not too bad on the time. If you have any questions, please let me know. Let's try to make sure that we're staying caught up on these assignments. Eventually, we are going to go back to class in person. I've got a confidence interval quiz I'm planning on doing next Monday, which Snowmageddon should end before then. So we'll eventually, by the end of this week, we'll have a practice quiz. I think I got one more lesson of this stuff, and then we'll do a review and then practice quiz. So it's all coming to an end pretty close. So quiz coming up, and then we got a few more chapters after that. Then we'll do a test. But I'll see you guys later.